Today we were going to present our research paper for EC242 course. The topic is an optimized DFT technology based on machine learning. Our team consists with me, Luna Yan, and Eric. So before we start it, we will introduce how we are going to navigate the topics we are going to talk about. We will cover some backgrounds, terminologies, and current studies, and how our paper advanced the current study, how we implement how the results comes out, and we will have some discussion and conclusion at the end. So first, within the increased complexity of chip designs, VLSI testing become significant to ensure the quality of the VLSI design, or the cost and the time of the VLSI testing needs to be reduced. We will have 5 objectives. The first one is testing quality or test coverage. We are going to maximum this as much as possible. And the second one is test time. Also, the test area, since we are going to insert the testing circuit in the waveform, so which means we will lose some yield. And also we need to consider to slow down the clock frequency for low power devices. Also, this enabled to lower the power consumption for more sustainability. Let's introduce some solution and some challenges we are facing. In DFT, full scan is very popular technique. Scan chain takes a lot of area. So our solution is to compress the scan chain as much as possible. So we need to configure the parameter in this architecture. And also we determine 2 parameters which are very important regarding the test quality and the testing time. They are scan chain IO port and the scan compression ratio. The compression ratio doesn't mean that you set it high, it will reduce time. Sometimes it doesn't work as very simple. It's not like linear, so we need to choose the best parameter solution. Design for testability is a solution that we insert some circuitry in the design without interface the functional design, but we are going to improve the test quality. So this solution was invented in 1970, but at that time the silicon device is too expensive and the design was very simple. This technology is not popular, but nowadays, because more and more companies and the testing department, they will use DFT. And on the right side, this is a disadvantage and advantage of the DFT. We will discuss what is testability. So we will have 2 concepts. One is controllability, and another one is observability. Those are 2 different ways to determine the how hard it is to control the input and to observe the output. So for combination circuit, it's super straightforward, and we already learned it in our lecture when we studied the ATPG, and we try to find some algorithm like path sensitization. We are trying to do some fault excitation. So if we want to control one signal stack at 0, we want to make it always behave 1. We will insert 1 OR gate which connect to another signal which is 1. So it will always set it as 1. So this is how we insert control points for the combinational circuits. And this table are more details about how to determine the testability for the combinational circuit. And for the sequential circuit, it's kind of complicated than the combinational one when we discuss testability. So we will introduce a concept of scan chain. So we have 2 different models. One is normal model and another one is test model. So if we want to, in the normal model, without lose any functionality in this design, we will insert the marks before the flip-flops. So all we need to do is just choose the marks as the original input sequence put into the input of the flip-flop. That is the functional circuit. But when we want to, in the testing mode, we need to choose the scan series input to the flip-flop. And this is testing mode. And we will have 2 different scan. One is a full scan and another one is a partial scan. The difference is how many flip-flops are going to be scanned. And then we have a control point. So as we already discussed, we just need to set different model for different tests. And for the observation one, we do the same thing.
So scan compression is a technique which reduces the test time of designs with high flip-flop counts. So these designs with high flip-flop counts, they end up having a very long scan chain length. And then with very long scan chain length comes very long test times. So the point of scan compression is to, again, reduce this test time. So then when we compress something, we will have a compressed scan chain length that is less than the original scan chain length, but as a trade-off, we will have a great number more of these compressed scan chains than we do the number of original scan chains. And a compression ratio is the number of generated chains over the number of original chains. So as you can see here on the right, we have a design with 4 times compression. So where we start off with 2 long scan chains, we end up with 4 or 8 smaller scan chains. And instead of having 12 nodes within that scan chain, we will now have 3 in each. So then continuing on with scan compression, there's a thing called a decompressor and a compressor. So the decompressor will take test patterns in from the tester, and it will take it in from these scan inputs, and then it will decompress them into multiple or a lot more of these scan chains that have been compressed from the original scan chains. And then just as we need to decompress the scan inputs, we need to compress these scan chain outputs to the actual scan data output ports. So then these things get compressed and then will go out to the assigned scan outputs. So now we will go over some literary review. So first, this first paper is about supervised machine learning recommendation system. So this paper goes over choosing the correct scan input output points and max length for the scan chains using machine learning. So here on the left, it kind of goes over scan compression again. So we have the decompressor and the compressor. So we have a certain number of scan inputs, and the decompressor will decompress them to a larger number of scan chains than we have scan inputs. And then the compressor will then recompress these scan chain outputs back into the actual scan output ports that we have. So then going through the method of creating these machine learning models to choose these optimal configuration for these scan compressions, we have first the data collection. So this data collection step will take in a number of different designs from industry, and it will generate multiple test cases per design. And then it will also extract features from these designs and put that into the data collection as well. And then given all these test cases that were generated, we will find the optimal amount of test cycles to, or the lowest amount of test cycles to reach the test coverage that we want to, the minimum amount of test coverage that we want to achieve with this model. And then once we have this data collection, we will then go to the machine learning model generation. And so all the data that they had collected before, they will use that for training and evaluation. So most of that data will go into training the machine learning model. So it will take all these test cases and features that were generated and train it given the test cycles that were the most optimal to create the best output to train this machine learning model. And then once they have that machine learning model trained, they will evaluate it using other test cycle and test case pairs. And then if it ends up having a good enough hit ratio, then it will be a valid machine learning model, and then they will use this machine learning model. And then here on the right, we can see that it's just an output of a given design that they put into a pre-trained machine learning model that they trained using these previous steps. And the output will be different configurations ranked from best to worst. And it will give the amount of scan input outputs and the max length, as well as two other figures. So the first figure is the degradation. So that is the amount or percent amount more of test cycles that will be needed in order to get the right test coverage given a lower rank of configuration. And then CL is confidence level, and that is just making sure that that degradation is, which is predicted, is as close as possible to the actual degradation that is occurring. So then the next literary review that we did was combinational compression architecture. So this paper went over a new compression architecture called Z-scan compression. So here on the left, we have an adaptive scan compression and decompression. So this allows you to control which scan inputs go to which scan chain that have been compressed scan chain. So there's multiple scan chains compared to the input scan inputs. And then we also have this masking data that we can use to mask which scan chains are actually mapped to the scan outputs. So this Z-scan compression builds upon this adaptive scan, and it is able to use a single scan input. It's able to shift those scan inputs serially in order to go into these linear feedback shift registers for the control data, the test data. And then we also have these cache registers. These cache registers will hold the control data, similar to the adaptive scan code that will choose which test data goes to which scan chain, and also which scan chain outputs will actually go to the actual scan output. And we can see just a comparison here on the top right with the serialized adaptive scan versus the Z-scan compression. So the Z-scan compression actually takes less cycles to compute. And given that it takes less cycles, it's actually able to compute it faster, and we can actually get a better compression than that of the serialized adaptive scan. And then finally, this new Z-scan compression is able to minimize congestion at the decompressor by splitting up that initial MUX multiplexer into smaller multiplexers, which you're able to control the optimization better of the different wires and area that are being used. And then next, a paper that we went over was the test vector compression techniques. So this paper kind of went over a large overview of different test vector compression. So here on the left, we have just the basic test data compression. So we have the tester that goes into the decompressor that then goes into multiple scan chains, which are a greater number of that than the scan inputs that we're actually getting at the decompressor. And then those scan chains will then be fed into the compactor or the compressor, which will then compress them to go back into the tester to see the proper outputs. So the reason that we want to do these test vector compression is so that the tester can use the least amount of memory to hold all these test vectors. And then also the biggest one is to reduce test time. So then another method of the test vector compression is here in the middle with the complete dictionary. So it will split up these scan chains into scan slices. and it will have these scan slices of n bits be represented by b-bit code words, where the b is a lot smaller number of bits than the n bits. So then we can, again, reduce the amount of memory that the tester needs to have. A drawback to this is the scan chains need to be manipulated, or the test cubes need to be manipulated in order to be different enough that the dictionary can stay within a reasonable size without needing b bits equal to n bits, basically. And then below that, we have a scan forest, which is another test vector compression technique, where instead of having one long scan chain, we can take that scan chain and split it up into basically a tree of sorts with roots and branches. So then that scan chain length will now be equal to the height of that scan chain tree. So that, again, reduces test time. And then finally, on the right here, we have the sequential linear decompressor, which uses a linear feedback shift register to represent these test vectors. So the tester actually only needs to send a seed for the linear feedback shift register. And then the linear feedback shift register can run autonomously and generate all these test vectors that will go into the scan chains. But the drawback to this is the tester is idle while the linear feedback shift register is running autonomously. So now we'll go to the methodology of the actual research paper. So this research paper aims to optimize two parameters, which is the scan chain input and output ports, as well as the scan compression ratio. And with modifying these two optimal parameters, we are targeting 5 of the test outputs, or the test optimizations that we want. So the one that's of the most importance is test coverage, and then we have test time, clock frequency loss, and then power and area. So here's the phases that the research goes through. So first, it will collect the data on what we have, and then it will save this data into a .csv file. And then we will create the optimal prediction and model selection for what we're doing. And then we will predict these parameters for the SIOs. And
Okay, so here is the implementation. First step, we are going to collect data. Since collect data always takes a lot of time, and we try to reduce the time spending in this phase, we are going to introduce Perl language to execute each simulation for different parameter configuration and store the results of the simulation in an Excel file. After that, we allow users to choose different parameters based on their experience regarding the size of the design. And then we come up with 7 SIOs and 6 scan compression ratios, so total 42 combinations. And then we're going to simulate for each parameter configuration of our design. And we store the output based on 5 different aspects in an Excel file. And the next step, we're going to choose the prediction model. In this phase, we are going to use Python because we are going to use machine learning. First, we are going to read the result from the previous stage, and we input those results for 5 different areas to the machine learning model. Those machine learning models are already trained because they are common used model, so we don't need to train them again. So only we need to do is to predict the output based on all the information we already have, the dataset, the test dataset we already have. We can have a different result for different model. Then we're going to analyze each model based on their error percentage. We can choose the most suitable model for each categories. And the next stage is to do the parameter prediction again, which we are going to use the model we already chose for the different categories. So let's say if we want to predict testing coverage, and in last stage we figured out the most suitable model for that for test coverage is KNN. So in this phase, we are going to use KNN to predict the results. Okay, so but in this case, in this stage, we're going to create another test set again. Based on the user experience, we can define a different range of parameter, and then we will generate different combinations for the parameter configuration. And we also do the same thing we already did in the first stage. We're going to store the result for those configuration simulation to the Excel file. Then we do the same thing in the second stage again to the different model. And then we read out the output of each parameter. And we store the result in the Excel again. So the last stage is to calculate and choose the best parameter configuration. So first, all we need to do is just collect all the data in last stage and normalize the data and sort them and remove the 40% of very worst case parameter configuration. We are not considering them. And then we calculate the distance between the best parameter configuration for the best output to the actual parameter results. And we will have the distance is our absolute distance, and we will choose the minimum distance for the optimal parameter configuration for each category. And then we also will do the comprehensive optimization configuration by calculate the distance for the ratio of each category and sum them up. This is for the comprehensive, and based on the comprehensive optimization result, we will choose the lowest 3 entries, the minimum distance, minimum error percentage as the most optimal configurations. And the result comes to 3 different, so 2 of them is we already in our implementation procedure for the model and for the parameter configuration selection. And the last one is to compare our parameter with a random parameter and to see how the selected parameter configuration is better than random ones. So first, we're going to select the optimal prediction model. So we have all the common machine learning module. And for this one, we are considering about the test time. And based on the rule we set, we will choose the most accurate prediction model by using a specific algorithm. And the conclusion is we chose these 3 for the test time prediction. And we will do the same thing for other 4 aspects. And then we enter to the last stage is to choose the parameter configuration. So at the left side is for each category, we will have different comparison. And if we only want to consider the test coverage, then we can just choose the first configuration by setting SIO2 and the compression ratio to 2. If we want to come to the comprehensive optimization, we will use the distance of the overall, and we will choose the minimum. So we come to the last results is to compare it with a random parameter configuration, and we look at the actual value here, and we do some calculation, and we come up the result that shows the test coverage and test time was significantly improved, while the area and power slightly decreased. But when we look at the prediction error, which is predictive value and actual value, and we do the error percentage calculation, we come up with 0.2767% is very good configuration, and the result comes very good.
So now we'll go through our discussion and conclude. So as we went through some other literature that we've done already, this literature provides like optimal full scan architectures, but it still has a need for that parameter configuration. And engineers still have to do that manually through trial and error, which consumes a lot of time and labor. And upon to the current study, this study was able to integrate machine learning to produce the optimal DFT parameter configurations, which will cut out that time and money that will be spent on the engineer doing trial and error. And then to conclude, overall, DFT's main purpose is to save time and money during post-manufacturing testing. So we should try to choose these optimal parameters to actually save time and money rather than spend more time and money implementing DFT. And when considering VLSI testing, test coverage and test time is the most important factors. And if we're really trying to save time and money, employing machine learning for setting up these DFT configurations is the right step in the direction to achieving this. And here's just a list of references that we have used throughout these slides. Thank you.
Thank you.